Hi, everyone. So I hope everyone can hear fine. Um, yeah, so as of the introduction, my name is Sonya and I lead the personalization team at Outbrain. And I will be talking to you about learning large-scale models for content recommendations. I will be covering both our offline layer, which is based on Spark, and our online serving layer, which is based on Elasticsearch. So a very quick introduction about Outbrain. Outbrain is a leading content discovery platform. We are basically helping people discover things that they find interesting and relevant for them. Just to show you a quick example of how Outbrain recommendations look like, if you're reading an article on CNN, you get to the bottom of that article, and then you are basically seeing two types of Outbrain recommendations. So then the first type is organic recommendations. These are basically links that will take you to other relevant articles on CNN. The second type of recommendations that we have are promoted stories, and these are links that will take you outside of CNN. So it would be either to different other publishers or other marketers or brands. We have offices in 14 countries, and our recommendations are being displayed on more than 9,000 websites and apps. Just to tell you a bit about our scale, this will be also relevant for the infrastructural part of our talk. We are serving 300 billion recommendations a month, and we are reaching 800 million people worldwide. So before we deep dive into some of the models and some of the infrastructure, I want to tell you a bit about our data, about our readers, and how we actually understand their interest. So it all starts with our NLP engine. This NLP engine is basically crawling two types of articles. So first, it's crawling all the articles where our recommendations are being displayed, and it is also crawling all the content of our potential recommendations. So this comprises of over 3 million new articles a week. And then this NLP engine basically generates a set of semantic features for each of these content pieces. And the semantic features, they have different granularity levels. So we have more general features such as categories, then we have some more specific features such as topics, and we have very specific entities that we also extract, for example, specific people or specific organizations. And so if you're looking at this story about the Big Bang Theory from CNN Entertainment, the features that would be extracted by the NLP engine would be, for example, for a category, entertainment, television. A topic, which is a more sort of granular feature, would be sitcom, and then we will have specific people such as Jim Parsons, Van Bialik, CBS, which is an organization. So this is the type of features we extract. And then from this content, we're actually able to aggregate our user profile. So our users each user have their own reading patterns. And throughout these reading patterns, we're able to generate the profile, which is essentially represented within the same space, within the same semantic space of categories, topics, and entities. So here you can see an example of a user profile. This is the categories parts of that user. And you can see that while one story will usually be categorized into one or two categories, here a user can have a variety of categories depending on what their interests are. So here's a user that is interested in television, investing, music, and so forth. And in the profile, we actually have also a score that says something about how, to which extent the user is interested within that topic. So then you can basically generate a user profile that has different levels of granularities, and here you're seeing a user that has been reading several articles like the one we've seen before, so they will be interested in television, sitcoms, CBS, etc., etc. Okay, so this is our data on the users. Now let's talk about our predictive model. So we divide our models into two types. One type are content-based models. So with content-based models, they will generally recommend content which is semantically similar to basically the topics the user is interested in. So if I have someone who is interested in music and technology and travel, this type of models would recommend content within this range of topics. So that's one type. The second type of models are collaborative models, and the basic principle behind those kind of models is if my taste matches someone else's taste, then actually what they liked will probably interest me as well. And for that, there are different techniques that generate such models. You have metric factorization machines, feature embeddings with deep neural networks. So these are the two types of models we're using. I do want to formulate a bit what is our machine learning challenge before we actually dive into the machine learning framework that we have. So what would be the machine learning challenge? We have our feature vector, which is comprised out of two things, basically. One is the user profile, the interest that you've seen before, and the current context of a user. So as you've seen in the example, someone is actually reading a CNN article at a specific point in time, and this would be our context. And according to these two features, these two types of features, we would like to predict for each potential recommendation, what is the probability of a click? Okay, how much this recommendation is actually relevant to the user at a specific time, at a specific context. Okay, so how are we doing our offline processing? And then we will actually move on to our online serving. So here is a talk that I've seen a while ago on YouTube. This is by D. Scully from Google. And in this talk, he was sharing his experience in technical debt in machine learning. And he was basically talking about the fact that in machine learning systems, you have very complex technology behind them, sometimes even more complex than other backend systems. And you need several principles to keep those systems robust. And two slides actually I wanted to share with you here. These are two slides from his presentation. So what he was describing is basically he divided the work of a data scientist into two parts. And the first part was the cool part of machine learning. So the cool part of machine learning is actually modifying your algorithms, hyperparameter tuning, thinking about new directions for your model, and so forth. So this takes some of your time as a data scientist. But actually then you have the rest of machine learning. And usually the rest of machine learning takes much more than the core part of machine learning. And the rest of machine learning contains different types of topics. It could be data collection, feature extraction, your deployment, your serving infrastructure, and all the basic components around your machine learning algorithms. And these two slides are actually supported by a data science report by Crowdflower from 2016 that tried to sort of measure how what data science spent the most time doing. And what they figured is that basically 60% of data science time would go on cleaning data and organizing it. Then you have almost 20% on collecting data sets, and you have a bunch of other stuff, but basically only 5% of your time is on the cool stuff, is on refining algorithms. And now I want to show you two examples that we actually encountered in Outbrain that support this. And this is the problems that I guess every company faces. And we wanted to approach those problems. So I'll give you two concrete examples of why these things take that much time. So let's talk about preparing data sets. What makes it a tough task? So for us, we have four main reasons why this is difficult. The first reason is that we have multiple data stores. Our data is either in Hive or in MySQL or in Cassandra, and it is that because it is generated by different flows in the system, and they're different, more efficient. So each data is generated in different flows, and it is more efficient to store it in different data stores. Secondly, what we have is that we have multiple data resources. So even if I'm taking only Hive, for example, then on top of that, we have many different tables. We have separate table for recommendations, then we have clicks, we have the user profiles, and again, this data is separated because it is generated by different flows in the system. What we also have is certain logic that we need to apply every time we generate a data set. Well, so it could be deduping, it could be filtering. We apply siloing, for example, if we want to actually train different models for different parts of our data. So this logic should be applied every time we generate a data set. And all of these things should actually happen in very high scale. So you've seen the number of our recommendations monthly. We have a very big number of records in all of our tables, and basically generating this takes time. So if someone just ad hoc wants to generate a model, takes 6 months of data, for example, this is something that can be very time consuming until the data is ready. A second example of sort of a component that may take a lot of your time would be evaluation. So for example, at Outbrain, we have over 15 evaluation metrics. These metrics are from different types. So we have more classical metrics like log loss, RMSE, AUC to check the accuracy of our models. We have metrics which are more associated with recommendation system and rankings, such as mean reciprocal rank. And we also have metrics which have to do with more on the business level. Okay, so they need to incorporate actually our pricing, and so these I would call sort of a simulation metrics of what will actually happen when our models are deployed in production. So these are we have different implementation of those metrics, and this is actually also time consuming for each data scientist to be implementing by themselves. Okay, so basically what we wanted to do is make sure that people spend more time, or even most of their time, on improving the algorithms and not on these peripheral tasks. So we've developed a machine learning framework that basically had two goals in mind. The first goal is agile research. Okay, goes without saying. Basically, this is what I've been just describing. We want to focus on modeling. We want to enable quick POC cycles. We don't want to implement from scratch all these processes that can be actually pre-computed. And the second thing that we want is to have robust productization. Okay, so once a model actually reaches some maturity, we are happy with the results of the model, we want to deploy it. We actually want to be able to, first of all, use the same code for retraining our models. We want to easily be able to retrain our models, because even when some model proves to be superior to other models, we want to incorporate them into production. We still want to make sure that new data that comes in actually refreshes the model. So we want to be able to retrain it. And we also want to have a mechanism that keeps our system robust, in the sense that before a model comes into production, we want to make sure that it's not corrupted, that the offline measurements meet a certain criteria. So I will talk about that in one of my next slides. So we have agile research and robust productization. Okay, so on a very high level about our framework, all our data resides in Hadoop. Top of Hadoop, we're running Spark, and then there's an applicational layer of Scala Spark that is where basically the components of the machine learning framework are running. And the framework has 5 components. First component is data collection. Then we have feature engineering. We have model training, offline evaluation metric, and model deployment. Okay, so let's talk about 1 and 4, which were actually the examples that I showed you before that may reduce our efficiency, right? So this is something that we want to be able to do on an automatic level. So how is the data collection component being implemented? Basically, what we have is ongoing hourly jobs, and they're responsible for 3 main things. So the first thing would be aggregating data from multiple resources. Then we are applying our pre-processing logic, and we're making these data sets available for model training and for model evaluation. And this is happening every hour. So basically, now each time a data scientists want to try a new model, they have this data set available up until the last hour. Model evaluation. So if you think about it, evaluating the model is not something which is dependent on the model. The only thing that we need to have is basically your predictions, right? It doesn't matter what generated those predictions. We have the predictions, we have the ground truth. We can apply all the set of our evaluation features on it. So actually this component, what it does is collects model predictions for a labeled test data set, applies a large set of evaluation metrics, and then these metrics are being reported to some centralized data store. And this data store actually serves 2 purposes. One is that a researcher can basically obviously check the results, but then it is also being used by this deployment component, which I will talk about in a second. And so what happens is that you actually have those two components, the feature engineering and the model training, which is the only thing that should be modified once someone introduces a new model. And usually it's actually the model training, so it depends on how big your change is, but often you don't really need to change the feature engineering part, but just the model training part. And then this thing that should be done is to implement only the interface of those two components. The implementation is either, SparkML, open source, or some homemade algorithms, and everything else is basically out of the box. So this is an example of how our simple model interface looks like. You have personalization model, and you need to implement two methods. One is add columns, which actually tells you which features from the data set that we have collected are going to be used in the model. Fit model is actually the logic of your model. Okay, so we talked about agile research. Basically, this is the interface that should be implemented. Let's talk a bit about robust productization. So as I've mentioned, what we want to do, even once a model reaches a certain state of maturity, what we want is to basically check how or make sure that the model is being updated with fresh data that comes in. So it's usually being done on a daily basis. And then so all this framework is actually being run on a daily basis. This is the same code that has been used for research. For the model deployment part, there is actually a coupling between this offline evaluation component and the model deployment. So we are basically having sort of a check or a threshold saying the model will be deployed only if they pass a certain quality check, basically whether the offline evaluation passes some threshold of some score or it's better than a certain threshold. If not, the model is not being deployed, and that way we kind of keep our system from being corrupted by some inaccurate model. Okay, moving to the serving layer. So you've seen our scale in general. These are the numbers that are interest us when we actually do the serving. So our throughput would be 35,000 requests a second, and we need to meet latency of 30 milliseconds. That is because we actually need to display our recommendations right at the same time with the page that is being loaded, the article itself. And another constraint that we have is that we actually have millions of potential recommendations from which we need to select the most relevant ones. So in terms of technology, what our decision was to actually use search technology or distributed search technology to implement our serving system. So to understand why search is actually compatible for this kind of problems, I will describe three main things that a distributed search engine, specifically Elasticsearch, can do, and then you'll gain a better understanding of why it's compatible. So the first thing is that Elasticsearch is able to efficiently apply filters over a large inventory. This is something which is not unique to Elasticsearch, but is general search engines can do it in a very efficient way. We'll talk briefly about that in a few slides. Why is this important to us? Because I haven't really described that in depth, but we do have a lot of market rules associated with our recommendations. So basically, the publisher can set some market rules saying, I don't wish to display certain types of recommendations, and also the content provider can say, I don't want to be displayed in certain types of publishers, for example, or I don't want to target users coming from certain geographies. So there are many market rules that should actually be applied for every request that we're getting. So doing that in an efficient way is one requirement that we have. Second thing is that search engines, well, that's what they do. They actually score the documents, right? They can apply a scoring function. And what is also quite nice is that they can apply a custom scoring function, and I will again talk about that maybe towards the end. So there is a mechanism where you can actually write your own scoring function, and this is something very useful to us. And the third thing is that because it is distributed, we are able to scale both for our inventory and number of requests. So basically either increasing our inventory or increasing our throughput just basically results in increasing the cluster, so adding more machines to our Elasticsearch cluster. So for those reasons, we have chose this architecture. Very quickly about what makes search engines efficient. Probably many of you know that. Those of you who are, have some basics in search. A search engine works based on something which is called inverted index. So for every document that is being indexed, a table is being generated when the key is actually the term, and the values are the documents that contain this term. And then once a query comes in, two things are happening. First of all, it is able to quickly filter out documents that don't have any of these terms of the query, and then for documents that have relevant terms, it is actually able to rank between them. So it's either by the count of the words or how popular these words are. There are many criteria for that, but basically these can be ranked. Okay, so search is compatible, but how can we actually do this reduction between a recommender system and a search system? It's not that straightforward. So what we're doing is the following. It is done in 2 steps. First, we're taking the content or all our potential recommendations, and we're translating them into a searchable index. So we're basically putting them as items within the index with all their metadata. And the next thing that we're doing is we're taking the user and the context, which is basically the input to our request, and we are translating this into a query. This query may contain the interest, it may contain other metadata. For example, if a user is coming from an article from CNN and there are some market rules, it will contain these market rules in the query. So all this information is being passed in the query. And basically, we have the scoring function. So first of all, we have the filters that are being applied for all, basically making sure that we're not getting any results that don't meet the market rules. And all the results that actually are eligible are being ranked. So here's an example of how a simple content-based model is implemented on top of Elasticsearch. This requires us to first basically index the semantics of an article within the search engine. So for each article, we have the features. Here's an example of only the high-level features, but it could be all levels of all granularity levels of the features. And then for a user coming in, we basically take the user profile, take the interest, and this comprises the query. So then Elasticsearch returns the most relevant recommendations. Okay, beyond content-based. So as I've mentioned, we're using collaborative models. We're using models which are much more complex than what I've shown, than the simple example of a content-based. And for that, we need to use the plugins option of Elasticsearch. So what is being done is basically we are writing a custom scoring script, which is a native Java. We are deploying it on the Elasticsearch cluster, and then the way to activate it is basically instruct the query. Do your scoring not with your regular scoring function, but rather with that certain code. So if you run an Elasticsearch query, it usually has basically two parts. The first part is your filters. The second part instructs how to derive the relevance function. And in that part, you are stating, okay, I want to use my code for that. This is the code that is being used for ranking. So what are the usages? I'll give you one example. We were working with user embeddings and item embeddings, which is very common for a recommender system. Which is very common for a recommender system. So in this case, the user, we have, again, an offline flow, which is part of the offline framework that I showed you before. And one of the implementations would be, for example, running factorization machines, generating embeddings. And then our online layer actually consumes these embeddings, and it consumes it in basically two directions. One is that the item embeddings are being indexed into Elasticsearch, so they're being part of the metadata that we store for each item. And on the other hand, we have the user embeddings, which are comprised into the query. And then we have, so this is what I'm showing here. And then we have the plugin, which actually computes the relevant score between those two embeddings. So then we have the ranking based on that. This is actually a paper that we've published on the last Trexis, on online recommender system and user modeling workshop. So we can, if you have any questions on that, we can take it offline, or just you can have a link to this paper. There are different challenges of incorporating embeddings. It is not that simple as just indexing the vector and indexing user item and indexing the user embedding and the item embedding. There are some challenges there. Key takeaways. First key takeaway would be invest in your machine learning pipeline. This is what you want to do if you want to make sure that you invest more time in the cool part of machine learning and less time on these peripheral tasks. Secondly, automate your periodic model deployment. Make sure that you have some control mechanisms and that basically keep your system robust. And thirdly, if possible, reduce your task to a problem someone already solved, maybe in terms of scale. So thank you for listening.